In the mid-1990s, a team of American aerospace engineers traveled to Russia to inspect a warehouse full of captured Cold War rocket hardware. When they reviewed the original Soviet telemetry data for these engines, the Americans declared the numbers mathematically impossible. This chart of American aerospace development was built on the luxury of infinite economic flexibility. To get to the moon, NASA relied on the raw power of open-cycle engines, pouring capital into giant single-chamber designs like the F-1 that lifted the Saturn V. Across the Iron Curtain, Soviet engineers faced a different set of constraints. Severe resource shortages and a rigid central planning system meant they couldn't simply scale up their physical designs. To match American thrust, they were forced to find a more efficient and far more dangerous method of propulsion. This divergence created a blind spot in the West. Because the U.S. program solved its problems through scale and redundant testing, American scientists lacked the context to believe the Soviets had achieved a level of metallurgical efficiency that bypassed their own models. Standard rocket engines operate on an open cycle. To power the pumps that push propellant into the main chamber, a small amount of fuel is burned in a preburner. In this layout, the exhaust from that turbine is simply dumped overboard, essentially wasting potential thrust. The Soviet alternative was oxygen-rich staged combustion. Instead of dumping the exhaust, this closed-loop system takes the superheated, highly reactive oxygen gas from the preburner and feeds it back into the main combustion chamber to be burned again. On paper, this is the most efficient path for a rocket engine. In practice, pumping superheated oxygen gas creates a literal blowtorch effect. When American engineers tried this, the oxygen-rich environment caused standard engine metals to instantly melt, leading to total structural failure. Since the wealthiest aerospace program on Earth couldn't stop the melting effect, they assumed the Soviets, operating with restricted resources, couldn't possibly have solved it either. The Soviet aerospace industry was a product of the central planning system. Rigid bureaucracy and limited capital meant that engineering choices were often dictated by what the state could afford to manufacture, rather than what was safest to fly. This pressure was exacerbated by the rivalry between chief designer Sergei Korolev and Valentin Glushko, the man responsible for engine design. They disagreed on everything, most notably the choice between toxic hypergolic fuels and Korolev's preferred cryogenic propellants. The feud reached a point where Glushko refused to build the large single-chamber engines Korolev needed for his lunar rocket. To get to the moon, the Soviet program was forced to rely on a complex cluster of 30 smaller engines on a single stage. Because these smaller engines had to generate immense combined power to lift the payload, Glushko had to extract every possible second of specific impulse. He was forced to attempt the oxygen-rich closed cycle that Western engineers had already written off as a death sentence. Political friction, rather than pure scientific ambition, pushed the Soviets to cross an engineering threshold the Americans didn't believe was reachable. To understand how the Soviet engines functioned, you have to look at how they managed the heat of the internal reaction. The solution lay in the development of classified Soviet stainless steel alloys. These materials were formulated specifically to resist the oxygen blowtorch effect, preventing the metal from oxidizing and melting, even under the most volatile internal conditions. These alloys allowed for perfectly precise closed-cycle valves. Designed with slide rules and analog mathematics, these components operated securely under superheated pressure, where any other metal would have seized. The result of this metallurgical breakthrough was a 25% increase in specific impulse over any hydrocarbon engine in the Western arsenal. Using only analog tools and proprietary chemistry, the Soviets had bridged a thermodynamic gap that the United States models suggested was a dead end. While the engines themselves were a success, the vehicle they were designed for was not. When 30 of these engines were integrated into the N-1 moon rocket, the macro system became unmanageable. The primitive analog computer system was unable to synchronize 30 separate power plants. Minor vibrations triggered cascading shutdowns, and the N-1 ended its career in a series of massive fireballs on the launch pad. Following the lunar defeat, Soviet leadership ordered the total destruction of all N-1 hardware. They wanted the failure erased from the industrial record. But the engineers involved recognized the value of what they had built. In an act of defiance, they secretly wrapped dozens of pristine engines in plastic and hid them in a forgotten warehouse, where they remained for 2 decades. The most efficient propulsion technology of the Cold War was effectively buried, waiting to be rediscovered by its geopolitical rivals. When the Cold War ended and American scientists finally pulled these engines out of storage, they were still skeptical. They took the 30-year-old hardware, strapped it to a massive modern test stand, and initiated a live firing. The control room watched as the telemetry data began spiking 25% higher than any engine NASA had ever flown. The impossible Soviet numbers were completely accurate. The discovery forced an immediate recalibration of American aerospace history. The telemetry proved the Soviets hadn't just matched Western efficiency. They had bypassed it decades prior in the critical field of propulsion. It was a realization that the laws of physics do not care about ideology. In the pursuit of survival, the Soviet engineers had out-engineered the very nation that had won the space race. The logistical response was immediate. The United States purchased the technology, adapting the Soviet design into the RD-180 engine. It is one of the great ironies of the 20th century. A technology built specifically to deliver thermonuclear weapons to the West became the foundational propulsion system for American national security launches. For years, the Atlas V rocket has been the workhorse of the U.S. space program, relying on this Russian-born metallurgical masterpiece to reach orbit. The engine that powered the Cold War didn't just survive the collapse of the nation that built it. It ultimately conquered the nation it was built to fight.